9.4 is on area between polar curves. And just like with 9.3, really the most difficult part in this section is identifying, number one, what this area is that we're talking about in a problem, getting a visual idea of what's going on, and then approaching the problem, deciding which approach you're going to take, because you'll notice there are different approaches depending on if there is symmetry or how you want to go about doing each problem, and finding the bounds that go with the approach that you're choosing. So we're going to spend a lot of time already looking at the graphs and analyzing them. I'm going to pull in Desmos a little bit here so you can see how the graphs look. But I really want you to spend the time in this lesson focusing on visualizing which area we're talking about, finding the area of, checking for symmetry, focusing on that intersection, and kind of thinking through different approaches on the problem. So one of the things to keep in mind, some sort of helpful hints or just reminders in general when we are finding the area between two curves, is you're pretty much always going to have to find the intersection points. These always are used in some way. Sometimes they're the bounds, sometimes they're used in a different way, but they're pretty much always going to be used. The second thing is to check for symmetry. Sometimes this will help you out. It will make the area easier to identify. It'll help you have to do less work or find fewer intersection points, things like that. Sometimes symmetry is going to work. Some problems don't really have symmetry, so it's not necessarily going to help you out, depending on what you're being asked for. You should always trace the function to see which direction that it's going. Which way is it moving? What area are we being asked for? And then making sure that all of the area that we are being asked for, we're including at some point in our integral. So these are things that you need to ask yourself when you're working on these problems. Sometimes you will need multiple integrals, and sometimes you won't need multiple integrals. So you need to be thinking through, do I need multiple integrals? Sometimes we do. Sometimes we can get the area that we're talking about with just one, but keeping that in mind, first of all, would this problem be easier if I split the integral? Or second of all, would it be easier if I didn't have to? Is there a way that I can do it without splitting the integral? And this last sort of tip, hint, sometimes we're still talking about, as we were first semester with non-polar curves, we're still talking about a big area minus a little area. And if that's true, you can just square each individual r value, which is r is a function of theta. You can square each of those and subtract them to find that integral as well. So thinking through, visually getting an understanding, coming up with the approach you're going to take for the problem, finding the intersection points, identifying the bounds on your integral, and then going through that process. So again, your calculator is going to do most of the physical calculation part. What you're going to be doing mostly by hand is figuring out your approach, integral bounds, etc. So let's look at a couple examples, and let me pull up Desmos really fast so that we can look at that for problem number one. All right, number one says to find the area between the graph of r equals -6 cosine of theta and r equals 2 minus 2 cosine of theta. So you can see those two graphs. The first one, r equals -6, that one is a circle. Sorry, -6 cosine theta. So that is this. Oh my goodness, let's try and at least make it, here we go, that's a little better. That's our circle, so that's this function. And then that leaves us with r equals 2 minus 2 cosine of theta being this function. So what we're being asked to do is to find the area between those two curves. So something that seems logical as a possibility of an approach is, well, what if I just found the area between them? So I'm really looking for this whole area, which I know you can't see all of because my browser is in the way. But I'm really looking for this whole area here. But what I could do is I could actually take this area that's labeled R1, and I could find that area, which may be easier, and I could double that area to get the area between that entire sector, right? Between that entire section of graph that we're talking about. But let's just stop for a minute. So that's my thought on approach. Maybe I can find the area of the top and then I can double it to find the area of the bottom or the entire area. Whoa. All right, so let's look at what's going on with our graph here. Let's let it run. So you can see, there we go. There we have our two curves. I'm going to let that run one more time because I want you to focus on which direction each of them are starting. So where do they start and which direction do they go? And then you can add that as arrows to your graph to help you understand a little bit more information about what's going on. So let's see if I can get that going again. So it looks like they're going counterclockwise. The radius looked like it actually started out at pi, or where we would see pi. Let's look at that one more time. So the radius is starting here and going this way, all the way around. The other function is starting, actually, let's let it run so that we can see. At what is the pole, it's starting at the pole and it's moving counterclockwise as well. So, starting at the pole and moving counterclockwise. So when I actually trace the area that's being formed, I'm actually going to be using both functions in a different way. It looks like this piece of the function is going to be formed using this circle. But once I get to this intersection, whatever this intersection is, then I'm going to shift and I'm going to be using the other equation to find this area. So you can see there's this little green piece of area and a blue piece of area, which likely tells me that I need to have two separate integrals. I need to find the bounds for each of those two integrals, and then I need to add those two areas together. And then after all of that, I need to double that area because I need to also find the area of this bottom section here. So lots to think through, but really start and figure out which curve is happening where, what area are you talking about. So let's talk about this green area first. And actually, regardless of the green area, we need to figure out where these two graphs are intersecting because that's going to help me find the point that I need to use, which is going to come into play in some way, likely in my bounds. So let's go ahead and do that part first. So let's find the intersection. Let's set these two functions equal to each other. So I'm going to set them equal to each other. If I get everything on the same side and simplify, this is going to give me that cosine of theta is -1/2, which means that theta is 2 pi over 3 and 4 pi over 3. And it's okay if you need to pause the video and work through those steps in more depth on your own. If we're talking about only the part of the graph that's in the second quadrant, we're going to be using this number, 2 pi over 3, is the angle that's happening at this intersection point. So that's going to come into play. So let's set up what we know about the green area, which I'm going to call R sub 2 first. So we know that that area is going to be the integral from something to 2 pi over 3 of the circle equation is -6 cosine of theta, and we're going to square that d theta. We're going to remember that we need a 1/2 in front. So this area is going to give us that little green piece. We need to figure out where that little green piece starts, or where our theta value starts forming. What is our theta value right here? And that is happening in this function. Well, what is the value of r right there? The value of r is 0. So I'm going to ask myself, when is r equal to 0 in the first equation? So I'm saying -6 cosine of theta equals 0. This is true when cosine of theta is equal to 0. And when is cosine of theta equal to 0? At pi over 2 and 3 pi over 2 in the first quadrant. This is the only thing that's going to matter. So that is going to be my lower bound. This point is not at 0, 0. Remember, the circle didn't even start at 0, 0. It started over here. 0 pi over 2 is the coordinate of this point. So this integral goes from pi over 2 to 2 pi over 3, and that's going to give me this area here. All right, let's do the same thing now for the blue area. Well, the blue area is going to start at 2 pi over 3. 2 pi over 3. And we need to know when it gets here, which looks like it's going to be pi. We can double check that. If I plug in pi, I should get 4 according to this point. If I plug in pi, I'm going to get 2 plus 2, which is going to be 4. So we're going to integrate this from 2/3 pi to pi itself. And what are we integrating? We're integrating the blue function, 2 minus 2 cosine of theta squared d theta. So we're going to take these two integrals, we're going to add them together and double it. So you could write that as one big long thing, or you could just find each area separately. So the area, and just because I want you to be able to check your work as you go, the area of the green portion should be 1.6305. The area of the blue portion should be 14.077. So when you add these together, your total area should be 15.707. And these were I already doubled these to get the bottom half. So your total area should be 15.707. So again, start by analyzing which part of which curve you need to use to find the area that you're indicating, or the area that you need to find. Identify where the points intersect. Use symmetry if you can. Figure out which direction the curves are traveling, where they start. And then ask yourself, do I need to use multiple integrals? Do I need to separate which part of the curve is forming where? This is going to get easier the more that you do it. I know it's really uncomfortable the first couple of times because polar is just something that you're not as comfortable with. So let's go ahead and work through a few more examples together. All right, looking at number 2, you can see the graph here. I'm also just quickly going to play this so that you can see how it rotates. They both start on the axes and rotate counterclockwise. We are being asked to find the area inside the circle, r equals 3 sine of theta, but outside the cardioid, r equals 1 plus sine of theta. So you can see that shaded region in the picture up here, and it's defined to be r. So right now, I want you to conceptually think, what approach should we take? That's the first part, right? Thinking through what approach should I take? Go ahead and pause the video and just think about that for a minute. How could I get this specific area without thinking about the bounds or the integrals, but what two areas am I using? Do I need to add them, subtract them? Should I use symmetry? Kind of think through that part. Okay, hopefully you have had time to think through an approach. The approach that I am thinking, especially because we saw that the curve rotates for both of them around the x-axis, is that what I really need to do is big area minus little area. I need to find the area of the circle over the region we're talking about. That's my bigger area, or my top area, and I need to subtract from that the bottom area. It seems like I can do this with just one integral. It seems like I could also possibly do half of this using symmetry and double it. That's definitely an approach. Since it seemed like this curve was just fully forming all the way around for both of these graphs, I don't think I'm going to use symmetry at all here. Again, even though that's definitely an option that you could use. So what we need to do now, we've come up with our approach. We need to know, what are these points? Where do they intersect? So go ahead and pause the video, set those two functions equal to each other, and find the r values where they intersect. So if I set 3 sine of theta equal to 1 plus sine of theta, I get that sine of theta is 1/2, which happens, especially looking at our graph, in the top two quadrants. So it happens at pi over 6 and 5 pi over 6. So those are going to be the bounds of my integral. I've identified which is my big area or my top area. That's my circle. So I can actually just go ahead and set up my integral. So I'm going to be integrating. The area is 1/2 of the integral from pi over 6 to 5 pi over 6 of the big area, or the top area, which is 3 sine of theta squared, minus the bottom one. This, I'm going to call this my purple area down here. So minus 1 plus sine of theta squared d theta. And then you're going to grab a calculator to input that, and that should give you that after you integrate this, you get pi. So walking through what we did, we decided on an approach, the circle area, subtracting out that overlapping region, which is the area from the cardioid. Then we figured out what are the bounds that we need for our integral. That's going to come from where these two curves intersect. So we found the bounds by setting the two functions equal to each other. And then we just integrated circle area minus cardioid area, subtract it, and then the area interval, or the area formula always has this 1/2 in front, and that gave us the value of pi. Let's look at a few more examples. All right, for number 3, I encourage you to pause the video and try and decide on your approach on your own. Do you want to use symmetry? Would it be helpful to use symmetry? What are the bounds of your integral? Where do these points intersect? But really just pause the video, take a couple minutes and come up with an approach. It may be helpful for you to watch this graph form. So it may be helpful to use Desmos and actually watch it, or use your graphing calculator, form from beginning to end. So go ahead and pause the video and think through a strategy for yourself on this problem. Okay, hopefully you have had time to think about an approach. And what I first want to do is just sort of highlight the area that we're trying to find. We are trying to find the area inside this curve, but outside the smaller loop. And obviously I'm not perfect at this, but we're talking about trying to find this big region area here. And what I noticed is that when I formed my graph, or when my graph was calculating, it started here and it went out this way. It curved all the way around. Then it came in and made this loop, and it ended right back here. So it's likely that I'm going to want to use symmetry. So I'm thinking maybe I can find the start and stop area over here to find this area, subtract out the piece of that loop that's there, and then double that area to give me the area that I'm looking for. Or an even better approach might be to actually just find the whole area on this half, including that inner loop, double that, which would give me the whole area of the entire thing, and then subtract out the area of that loop on the inside. So what I need to do first, I need to figure out where does this portion start and stop. So I need to figure out what those two bounds are, and how do I go about doing that? The first end point, or the first bound of my integral, I think is pretty clear. This looks to be the point 6 comma pi over 2. And I could just plug pi over 2 in to confirm that that is that ordered pair right there. That polar coordinate is right there. So the bottom portion of my integral is going to be pi over 2. What I need to figure out is, what is this? So I'm asking myself, what's happening with r when I'm there? R is going to be 0. So that's where I need to stop, but I need to figure out what theta value gives me this r equals 0. So what I'm going to do, I'm going to make some room, or I'm going to just come over here. I'm going to say that I want to know when r is equal to 0. So I want to know when 0 equals 2 plus 4 sine of theta, which means that I want to know when sine of theta is equal to -1/2. This is true when theta is 7 pi over 6 and 11 pi over 6. Looking at these two, this is almost all the way. It would have already come back around. So I'm going to use the first time that that happened is the bound that I'm looking for. So I'm going to be integrating from pi over 2 to 7 pi over 6. And I'm going to be integrating r squared, 2 plus 4 sine of theta quantity squared d theta. And when I plug this in on my calculator, don't forget to divide by 2 after you integrate. I get 17.762. So that's the area of the entire left-hand part of the graph, including that overlapping region that we need to subtract out, that inner loop right here that we're going to need to subtract out. So let's find the area of that inner loop. Or better yet, let's double this. I guess I could have just not multiplied by 2. Let's double this. That's going to give us 35.525. And then we're going to subtract out the entire area of this inner portion of our graph. This here, let's draw down here, this inner portion of our graph. Well, we know that this starts where the last integral left off. So this starts forming at 7 pi over 6. It goes all the way around, and we actually know where it ends. It ends when it gets back to that exact same spot at 11 pi over 6. All right, so now I can set up my small loop. That's going to be the integral from 7 pi over 6 to 11 pi over 6 of 2 plus, oops, don't forget my 1/2, 4 sine of theta quantity squared d theta. Now remember, for this particular area, we aren't doubling it. This does give us the entire loop, and that's the area that I want. So don't forget, after you integrate this, to divide by 2, which should give you 2.174. So our total area outside the inner loop but inside the outer loop is going to be, when I take this 35.525 and subtract this 2.174, and that's going to give me, my total area is 33.351. So really focus on the approach. You may have taken a totally different approach than I did on this problem, and that's fine as long as you're encompassing the area that you're being asked to find and you're doing it with bounds that make sense for your integral. Let's go ahead and look at number 4. All right, let's check out the graph, the rotation order that number 4 has. So here we can see that curve forming counterclockwise around the axes. The circle, which we didn't see in the video, but starts at 0 and rotates counterclockwise, just like the unit circle. And we are being asked to find the shared area of both graphs. So that means we're being asked to find, so first thing, right, identify the area. We want to find this area in here. So if you want, you can go ahead and pause the video and see if you can find the approach that you want to take on this particular problem. Okay, hopefully you have had time to think about this. What I notice are my 2 intersection points here, and that between those 2 points, we are using the graph that is not the circle, which means that I'm actually forming, because of how polar graphs work, I'm starting, my radius is rotating this way based on theta, and this green area is totally coming from, or is coming from this part of our function, this particular function. Then everywhere else is being formed by the circle. So I know that these are going to be my key intersection points that I'm going to need to have to find. And I also realize that I'm probably going to have to split this into 2 integrals and find the area from in between these 2 bounds, and then find the area using the circle portion outside of those 2 bounds. So starting at this point and going around for the circle. Let's use a different color for that. Starting at this point and going around for the circle. So let's think through this. So let's go ahead and find those intersection points. So we want to know when 3 equals 4 minus 2 sine of theta. That's going to be when is sine of theta equal to 1/2. And that's going to be true when theta is pi over 6 and 5 pi over 6, right? Because we're looking for those top 2. So this is going to be pi over 6. This is going to be 5 pi over 6. So we actually just found all the information that we need to find the area of that green portion. So let's go ahead and do that part first. So here's the setup for that integral. And when we evaluate that on our calculator, don't forget about your 1/2 in front. We should get that area is 5.859. Now all we have to do is find the area of that red portion that I didn't darken with green, and then add these 2 areas together to give us our total area. So we know that one of the bounds for the area that we're finding now is 5 pi over 6. We need to get all the way to figure out where that ends. The problem is I can't actually go all the way around here, because then I'm going over 2 pi radians, and that's going to get really confusing for my calculator. So what we're going to do is we're actually going to find the area of this half, which looks like it's going to stop at 3 pi over 2 since it's on the axes, and then we're going to double that. So let's set up that integral. So we're going to find the area of 2 times 1/2. Yes, I know that those go away, but let's still see it because we're doubling. And the area formula has the 1/2. We're starting at 5 pi over 6, and we're ending at 3 pi over 2. And we're now using the circle, which is just 3 squared d theta. And when you plug this into your calculator, you should get 18.849. 18.849. And now, last step, we need to add these 2 things together, which will give us our total area, which is going to be 24.708. All right, last problem. Let's go ahead and see this graph form itself so that we can see the direction in which it is moving to get an idea of what approach we want to take here. So here we go. All right, so we're seeing it's rotating this direction. So I tried to put some arrows on there to indicate the direction that it is rotating to help us get an idea of what's going on. And the question is asking us to find the area that's inside the rows and outside of the circle. So we are being asked to find, let's use a highlighter. We're being asked to find this area. We could obviously use some symmetry here, and that's the approach that I think I'm going to take. I want to find the area that we're talking about just for one specific petal, and then I want to make sure that I multiply that area by 4 to get the total area overall. A little bit of a problem is that I can't actually, this whole petal doesn't form all at once, only the top half forms. So actually what I'm going to need to do is I'm going to need to find this top half area. I need to find this area and then multiply that by 8 to get that same area for all of the different pieces. Now, your gut might be saying, well, we could just find the area of the whole flower and subtract the area of the whole circle, and that would give us the area that we're talking about. But that's actually not true because there are parts of the circle that aren't overlapping, so you would be subtracting out too much if you took that approach. So I really do think the best approach on this problem is to find that black area that I just darkened and then to multiply that piece by 8. So again, our approach is going to be to find the area of half of one of those petals, subtracting out the circle component, and then multiplying that area by 8 to give us all of our petals together. So we need to find the intersection point. That's going to be a big deal in this problem, and the only intersection point that we care about based on our approach is the very first one, which is happening right here. So we want to know when 2 equals 4 cosine of 2 theta. So go ahead and pause the video and solve that out and see if you can find your theta value. So cosine of 2 theta is going to be 1/2, which means that 2 theta is going to be pi over 3, again, because we only care about the first intersection point, which means that theta will be pi over 6. So we just found the top half of our bound, pi over 6. We did see that this petal starts at 0. And what we need to do, the petal area is bigger than the circle area, so we need to do petal area, which is 4 cosine of 2 theta squared minus the circle area, integrate that with respect to theta, d theta. And then we want to take that entire area and we want to multiply it by 8 to give us all 4 petals, since this area is really only half of one of the 4 petals. So go ahead and grab a calculator, type that integral in. You should end up getting that this area is 15.305. So to wrap up 9.4, things to think about. Visualize, get a visual idea of what's happening with the graph. Figure out where it starts, which direction it's rotating, darken the overlapped region that you're talking about. Know that the intersection points are going to be used in some way on every problem, whether that's in the bounds of your integral or in another way. So you're going to want to find those intersection points. Identify if symmetry is something that you can use and will help you on this problem. Determine if you're going to need to have one or more integrals in order to piece together the area that we're talking about. And when necessary, double, triple, divide to get the appropriate area that you're talking about. So write down any questions that you have, and I look forward to supporting you on this in class. Thanks for listening.